Welcome everyone to today's live session. Today we are going to be talking about vegetation phenology, and we are going to particularly be using optical data sets, the Sentinel-2 optical data set to run through phenology. Now, phenology is a study of plants and animal life cycle, particularly the physiology of the physiological development of plant growth. It helps us to understand when planting season starts, how the season progresses, and at what time it ends. It also makes it possible for us to monitor crop performance to see how crops perform during a particular year or a particular planting season. It makes it possible to be able to schedule fertilization, pest control, and even harvesting. It could be done annually, which makes it possible to understand how a particular area develops its agricultural season from beginning to end. Now, there are more information on phenology. We could always go through literature to learn more about what phenology is all about. But in this notebook, we are going to be going through using NDVI to run the phenology for an area in Nigeria, particularly Batitin area of Plateau State, Nigeria. Now we'll use NDVI to be able to run the phenology, and to do that, some of the things we are going to be able to do is to load the crop mask analysis ready data sets from Digital Earth Africa. We're going to calculate vegetation indices, particularly the Normalized Difference Vegetation Index. We'll use that indices to calculate the phenology, and then we're going to be able to analyze the phenology of the study area. Okay, to start, first of all, I'm going to clear my kernel, all outputs from my kernel, and restart it. Okay, so the first thing we're going to do is to load in the data sets that we're going to make use of for this analysis. We are loading the data cube, the matplot library, the NumPy, pandas, and xarray. We're going to be able to bring in the band indices. Of course, we require the Dask to ensure that our scripts run properly, the data handling, the plotting for the maps, as well as the temporal statistics and the XR phenology. So we would run this. Now, having done that, the next is to connect to the data cube. And we're connecting to the data cube using the app we are going to call Vegetation Phenology. So I'll go ahead and run this line of script. Now, next thing we are going to do is to determine our analysis parameters. We'll first of all determine the vegetation proxy we are using, which in this case is NDVI. We can also make use of the Enhanced Vegetation Index. So we could use NDVI or EVI for this notebook. We are using the NDVI. Next, we are going to specify the latitude and longitude for the central point of our study area, and then we'll define a buffer which will give us the entire extent of the study area. We'll also define the time range we are going to be using, the resolution of the data sets, the output coordinate system, the Dask chunks, and the output directory from which our results will be saved to. So here are the parameters. The vegetation proxy we are using is the NDVI. The latitude and longitude for Batitin in Plateau State, Nigeria. The center latitude value is given here and the longitude value is given here. We're going to be using a buffer of 0.02 to define the study area. The data sets we want to work with will be from 2017 to 2020. The image we are using is Sentinel-2 data set, which is optical, and the optical data set is 20-meter resolution. The output coordinate system is given as the EPSG 6933. We've defined the dash chunk there, as well as the output directory, which all our results will be saved to. Now, having defined all those, we can run that. The next we'll define is the extent of the area. Now, in this, we have only just determined the latitude, longitude, and the extent of buffer. Now, we'll use that buffer to calculate the extent of the area using these codes here. And we'll run that. Now, having set up our data sets as well as the extent of the area we want to work with, the next is to set up our memory by creating the local DAS cluster. So we'll go ahead and also run this script. Now we can view the area that we have selected based on the parameters that we chose in the third and fourth lines of script. We're going to display the extent of our study area using this line of script. Okay, so here is our study area. It's like I said, it is located in Jos Plateau State of Nigeria. It's an area that is well known for agriculture. We can also see that there is a water body there, which means that this water body feeds almost year-round agriculture in the study area. The area is known for planting vegetables, especially things like garden egg, green peppers, cabbage, carrots, green beans, and so on. A lot of vegetables are gotten from this area in Nigeria. So moving on, we are now going to load the Sentinel-2 data, and we are loading from the analysis ready Sentinel-2 data set using the latitude and longitude values we have specified in previous cells, the time range, the resolution, and all these other parameters. So we'll just run this. Now remember, we are loading in image from between 2017 to 2020, given as that is the time range we're working with. So we have dimensions of time stamps data sets of 267, given this X and Y values, right? Now, having loaded the Sentinel-2 image, the next thing we want to do is to load in the crop mask image. The crop mask image is also another analysis ready data set that is provided by Digital Earth Africa. So we are going to run this kind of code to bring in the crop mask data for the period of 2019, which is filtered and using the nearest neighbor resampling technique based on our DASC chunk that was created earlier. And so we will run this and have it plot in a cropland extent map. Right. So here is the cropland extent for our study area based on the 2019 cropland extent dataset. Now the areas that are in green shows us the areas that have agricultural activities or crop data, while the areas that are in white have less crop data. Now this cropland extent map data set is what we are going to use to mask out the rest of our data set. So in the next line of code, we are going to use this cropland extent to create a mask for all our Sentinel-2 data. So we run this one, and it has run the masking of the data set. Now we can display some. Now remember, when we brought in the Sentinel-2 data, we had 267 time, but we're only going to display about 4 of them. We'll display time 1, time 22, time 44, and time 17, just so that we'll see how the crop mask data works with the Sentinel-2 images that we have in this series. So we'll run that. Run. Okay. So here is our study area at this time intervals, timestamps given. This is the area in first, this is January, sometime January 2017. This is in July 2017, no data. We have that of December, November 2017. We have 2018 February. So based on these timestamps, these are the available data sets. Now we have been able to bring in our Sentinel-2 data sets as well as the crop mask and use that to mask out all the extent of area in all the images we want to work with. Now, the next thing we need to do is to compute the vegetation indices. And like I said, we are going to be making use of NDVI. You could use the the Enhanced Vegetation Index, which is given by this formula 2.5 times near infrared minus red divided by near infrared plus 6 times red minus 7.5 times blue plus 1. So you could make use of this for the Enhanced Vegetation Index. However, we're going to be making use of the NDVI, which is the Normalized Difference Vegetation Index, which is given by the near infrared minus red divided by the near infrared plus red. So this line of code, first of all, allows us to define our indices based on the vegetation property we have stated in previous cells. So we'll just select this and run it. Right. So we have defined our indices given there. Now we want to calculate the vegetation proxy, which is the NDVI, for all the Sentinel-2 images we have between 2017 and 2020. So we are going to run this. This is going to take a little bit of time to run. So we'll just be patient. Remember, we're calculating this for about over 200 images. So it's going to take a little bit of time. It could take up to a minute or two to run. So we'll just patiently wait for it to complete running the NDVI for all the images we are making use of. We're still waiting on it. Still running. Great. So it has been able to compute the NDVI for all the images we have between 2017 and 2020. And you see that it took a total of 2 minutes, 1 second to run the NDVI computation. Now, next we want to plot the NDVI for the images we have in a graph using this code here, which allows us to plot it in a zonal mean of vegetation time series. So let's run that. Right. So this gives us the NDVI for the study area across the data sets we have between 2017 and 2020. Now we can see that there are so many data values given here. Remember, we had about 260 something timestamp data. And we also have some very extreme values, like here where we have extreme low values, also likewise here. Now we need to carry out a smoothing on this data to ensure that we are interpolating data and getting a much smoother result. Now the next code is to carry out a smoothing to interpolation activity on the time series data that's, or the NDVI data that we have here. And so using this code, we are going to resample the data set to give us a smoother NDVI curve. So we'll run that. Now we can now plot the new NDVI curve based on the smoothed data sets. And we'll run. All right. So now we have a smoothed NDVI data set with values from between 0.05 to about 0.4. Right? Unlike before, where we had very low values that were in negatives and they were outliers. So we have a much smoother data set with a 2-week interval so that we have a smoother NDVI curve. Now we can export this NDVI curve into a table, which would also be saved into our results folder. So we'll run that, and it creates the NDVI in a table that will also save to the results folder. Now this NDVI values is what is going to be used to calculate the phenology. So now the next thing we are going to do is calculate the phenology. And this will be done based on the day of year of the start of season, the day of year of the peak of the season, the day of year of the end of the season, the NDVI values at the start of the season, NDVI values at the peak of the season, and NDVI values at the end of the season. Now, it also calculates the minimum value of NDVI in the season or during the season, the length of the season, the amplitude of the season, the rate of greening, and the rate of senescence. So these are the parameters that are going to be calculated in running the phenology for our study area. Now, the first thing we will do is to, first of all, define all of those parameters, all of those terms. And that is what is given in this set of code. All right, so having defined all of the terms, the next we want to do is to calculate the phenology for all of those terms. And it will determine that based on the year. It will first of all eliminate any year that does not have information. So it's first of all going to use a slice to remove incomplete years from the list. And then it's go ahead and calculate the phenology statistics for each of the data sets available in the years that we have. So we'll run this. Now can see that it has calculated the phenology values for each year between 2017, 2018, 2019, and 2020. So we can see the start of season. It shows here that the start of season in 2017, the day of the start of the season is the 92nd day of the year. The peak of the season was on day 274. The end of season was day 358, close to the end of the year. Of course, this gives us the NDVI values at those days in the year given here. The lowest NDVI values during the season is also given. Length of season, the amplitude, the rate of greenness, and the rate of senescence are also given for each of the years. If we look at this, we can see that in 2017, the season started later than in 2018. And in 2020, it was about the latest year from which there was the season started. So moving on, we need to plot this in a graph. For now, we're only just seeing it as a list of data sets, but plotting it in a graph makes it more clearer. So this set of code is going to plot the phenology for each of these years in a line graph. So we'll run that. Right, so this is the phenology for our study area in the year 2017, 2018, 2019, and 2020. And you can see the trend in agricultural or vegetation phenology in the area, showing when the season started, the values at the peak of the season, and end of the season. Now, we'll note that regardless of when the season started, and we noted that in 2020, we had the latest stats in the season. The peak of the season too, in 2020, we had the latest peak of season, but we can see that the seasons ended almost all at the same time in the year. But we also see that 2019 had the highest NDVI even at the end of the season. So the gives us a graphical representation of the phenology across the 4 years of study. Now, we need to convert this phenology data set into a table, which would also be saved into our working folder. So this helps to convert this phenology data set into a table data set. So we'll run this. And so it creates a table of the phenology, giving us the same information that was used to plot the graph. And now this saves the outputs into the working folder. Now this is all fine and good, giving us it gives us an explanation of the phenology across the year, but it will be more visual if we're able to see the per pixel phenology. And so next we are going to calculate the per pixel phenology using the data sets provided in the previous cells. Now, this allows us to, first of all, remove incomplete years and run the phenology per pixel for all the data sets between 2017 and 2020. So go ahead and run this. Now, we'll pick a year. We can choose any year. Let's pick the 2020, the year 2020. Can choose any of the years in our analysis range between 2017 and 2020. For this, we're using 2020 and run it. Now, we can now plot the phenology for the year 2020 using this. So it's going to plot the start of season data, the peak of season, the end of season, the length of the season, the amplitude, the rate of growth, and the rate of senescence, and give it to us in a graph, in the pixel analysis. So we'll select that and then run. Right. So here is the phenology for 2020, and we can see the start of season, the day of year of start of season, the day of year of peak of season, the day of the year of the end of the season, the length of the season, which is the number of days in the season, the rate of growth, and the rate of senescence. Now we also see the NDVI values at the start of the year, the NDVI values at the peak of the year, the NDVI values at the end of the year. Now, if you observe, you can see that at the peak of the year, the NDVI is generally high, right? And then you can definitely see areas that have the most greenness, given the start of the season, peak of the season, and even in the end of the season. Now, this shows us the number, what day of the year the seasons began. And for most parts of this area, you see that the start of season was somewhere between the 50th day and the 100th day of the year. The peak of season in most areas was between 150 and 200 day in the year. Well, mostly between maybe 200 to 250. And the end of seasons were mostly from 250 to 300 days of the year. So you could see that given there. Now, most periods in the study area had a season that had length of somewhere between 250 to 300 days, even though we can see that some parts had fewer days of season, possibly less than 100, but most of those we can see are falling around areas that are water body. The rate of growth and the rate of senescence is almost equal in both areas, showing that the rate of growth is around 0.05, and the rate of dryness or senescence also giving around minus 0.05. So in conclusion, we see that we are able to study or see the pattern of the growing season in the study area. We can clearly see the number of days where vegetation is at its peak in the study area. And we can see that most agricultural activities run from around March, April in the year into December in that study area. So this helps us to understand the nature of agricultural activities in that study area, especially given the nature of that area, that it's a major area in crop production in Nigeria. So phenology statistics are a powerful way to summarize the seasonal cycle of plant life, and using the per pixel plot of phenology helps us to understand the timing of vegetation growth and senescence across a large area. Now, for example, we can use it to assess how growing seasons change, where we can see that in 2020, the growing season started a little later compared to 2017 and the other years before it. So here are some additional materials on phenology that we can feel free to explore at our time. And if you feel like running through this again, you can go through running the phenology for the optical data, which is what I've just done, or even running for radar, using radar data sets, the Sentinel-1 data. So I would urge us to explore running the optical phenology as well as the radar phenology at our own time. Thank you. Thank you everyone for listening.
Thank you so much, Phoebe, for this great presentation. Actually, everybody's clapping for you. I wish to ask any participant who has a question, please. This is your time. Also recognizing those ones who joined in the middle of the session, that all the recordings will be shared with you for follow-up. Thank you so much, everybody.